So proper forwarding circuits should be added to the existing pipeline architecture to implement this operand forwarding. This will add to the complexity of the circuit. Even then, operand forwarding is the best solution for data hazard. Now suppose we have one more instruction I4 which is also dependent on the same register R1. In the fourth cycle, when our fetch unit is free, we can start fetching this instruction. But in the next cycle, if we try to decode this instruction, operands will be accessed from the registers R1 and R9. But the data is being written to register R1 in the same cycle, hence the data is not available yet. It will be available only at the end of the fifth clock cycle. So here we are trying to access data from the register and the data is not available within the register. Now do we need to use operand forwarding? Here we are writing to the register and reading from the register in the same clock cycle. So here there is one more solution available. If we can arrange the registers such that a write always happens in the first half of that clock cycle and a read always happens in the second half of the clock cycle, then in the first half of the fifth clock cycle itself, the content will be written to the register R1, and in the second half of the fifth clock cycle, we will be able to read the data from the register R1. Hence, we can execute I4 also without causing data hazard and producing the instruction out in the next clock cycle itself. So if a data hazard occurs because we are trying to read from the storage and write to the storage in the same cycle, then it can be solved by arranging the storage such that a write always happens at the first half of the cycle and a read happens at the second half of the cycle. Now, if a data hazard occurs because one instruction is dependent on the data produced by a previous instruction, and if that data is not available within the storage, then but if the data is available somewhere within the pipeline, then operand forwarding can help. Now, is there a situation where operand forwarding cannot help? Suppose we have a load instruction. Suppose we fetched this instruction in our first clock cycle. In our second cycle, we accessed the operands from the register. Here the content of the register is the address of the memory location, which is 1000. In the next stage, in the execution stage, suppose we have an effective address computation required. That effective address is computed here 1000 plus 5. In the memory stage, we will access the data from that memory location corresponding to the effective address. The address is 1005. Let the content of the memory location be 10. This data will be accessed in this memory stage, but it will be written to the register R1 only at the end of the fifth clock cycle, at the end of the write back stage. Now suppose we have an arithmetic instruction, an add instruction, which is dependent on the data in the register R1. This instruction can be fetched in the second cycle, but in the third cycle, if we try to decode it, our required data is not yet written to the register R1. So here we are trying to access the data from the register, but it's not available within the register. Now whether the data is available somewhere within the pipeline, this instruction needs this data for execution at least in the beginning of the execution stage or at the end of the decode stage, and when this instruction is at the end of the decode stage, the load instruction is at the end of only execution stage, mean only the effective address is computed, the data is not yet accessed by the instruction load, so our required data is not available with this instruction. The data becomes available with I1 only at the end of the memory stage. When I1 completes the memory stage, our add instruction completes its execution, so there is no use. So here, operand forwarding directly cannot help. We need to stall for at least one cycle. We cannot execute it here. If we stall for one cycle, then in the next cycle, by the beginning of the next cycle, this data becomes available with the load instruction. Now by forwarding from the memory stage to the input of the ALU stage, we will be able to execute this instruction. So in some situations, operand forwarding cannot help, then pipeline stalling has to be used. So here it leads to the wastage of one CPU cycle. And again, if we need to avoid pipeline stalling at a hardware level, there is no solution. Then at software level, we have one solution by the compiler called rearrangement. In the previous case, in between these two instructions, if we can bring one instruction such that if this movement will not affect the functioning of the program as a whole, then no need to stall the pipeline. By the time the add instruction is in the execution stage, the data becomes available with I1 in the memory stage. It can be forwarded. So no need of pipeline stalling. Instructions can be processed out in each clock cycle. So these are the solutions used for data hazards, and these kinds of solutions, especially the operand forwarding, is mainly used for the type of data hazard in which one instruction tries to read some data which is written by another instruction. In other words, one instruction is expected to read some data only after a write, but by using pipelining, we are trying to read that data before the write. These kinds of data hazards are called read after write data hazards. We are expected to read after a write, but we are trying to read before that write. Such hazards are called read after write hazards. With this kind of five-stage pipeline architecture, where we consider one cycle for each stage, only read after write hazards are possible. But there are other two kinds of data hazards which we will discuss in the next video.